everyone, this is Chapter 4, Section 4, Part 3. I'm titling this section Reciprocal Functions in Disguise because we're going to look at some rational functions that actually are reciprocal functions, but they might not look at first glance, but through long division or factoring, they can take the form of a reciprocal function. All right, so the first key concept is we're going to look at a rational function whose numerator and denominator are both linear, and we're going to use long division to rewrite it so that we can see the translations or the stretch in its proper reciprocal form. So it doesn't always have to have linear polynomials in the numerator and denominator. Sometimes it'll also be a reciprocal function even if it's not linear. But the first case we will look at is linear, and then we will be able to put that into proper form so that we can see the asymptotes. So here we have just generic form y equals ax plus b over cx plus d. We know that these are linear because there is no exponents on either of the x's there. And we learned in Chapter 3 how to rewrite this as the quotient plus the remainder over the divisor. So in this first example, we have two linear polynomials in the numerator and the denominator. And through long division, we can try to rewrite this. So I'm going to put the dividend 4x plus 3 underneath the long division symbol and my divisor on the outside. And remember, through long division, we just look at that first term here in both polynomials. I'll circle it. We're looking at 4x divided by x, and 4x divided by x is 4. So I'm going to put that over its like term. It's a constant. And now I'm going to multiply this 4 through both of these terms. So I end up with 4x plus 4. And then I'm going to subtract this entire polynomial from the one above it. So 4x minus 4x is going to cancel. That's why we did that. And then 3 minus 4 is going to give me -1. So if I rewrote this function, f of x, I could say f of x equals the quotient plus the remainder over the divisor. And I'm just going to rearrange the furniture a little bit here so that we can definitely see the reciprocal form. I'm going to say -1 over x plus 1 plus 4. So I just used the commutative property of addition, and now I can see that our k equals 4, and that means up 4 units. And h here equals a -1, and that means left 1 unit. And a is a -1. So we do not have any stretch or compression, but because of that sign right there, we do have a reflection. So we can see that our vertical asymptote is going to be at x equals -1. That's what's going to cause the 0. And we're shifting up 4 units, so our horizontal asymptote is going to be y equals 4. And so the easiest thing to do when graphing the reciprocal function is always graph those asymptotes first. So we know that our horizontal is y equals 4, and our vertical is x equals -1. Everything is going to be symmetrical around that point right there at the intersection. Normally, we would think our function would be up here and down here, but because of the reflection, we're actually going to be over here on the left and down here on the right. With no stretch or compression, we would expect to go through these 2 points. In other words, move over 1, down 1, and move to the left 1, up 1. But you can always make a table of ordered pairs, and sometimes that's the easiest thing to do. So if we just try a few points, and it's okay to use the original form. In fact, it might be a little bit easier. 4x plus 3 over x plus 1. If I substitute in, say, -2 here, that's a negative 8 plus 3 is negative 5 over a negative 1. That equals positive 5. So at x equals negative 2, we would expect to be at positive 5, and that's exactly where we're at. And if I go to the right of this intersection here over 1 unit, that would be x equals 0. So if I plug in 0 there, I have 3 over 1, which is 3. And that's exactly where we would think we should be. And you can calculate other points, or you could just follow the standard parent function. If I'm a half down, I should be over 2, and it'll just get closer and closer. I actually want to put that in red. And then go down to here. So we'll just infinitesimally get closer and closer to these asymptotes on both sides here, and we'll be symmetrical over that point of intersection. All right, let's take a look at another example where the numerator and denominator are linear. This may look simpler, but in fact it's actually a little bit more rigorous here. And the reason is, and you may recall this back in chapter 2, in order to look at translations off of that x variable, x has to be alone. We cannot have that 2 in front of it. So we do need to begin to factor out that 2. If I factor out that 2 using the distributive property in reverse, then that 2 is actually multiplying x minus 1/2. So I'm going to rewrite this then as 3/2 x as the numerator over x minus 1/2. Looks like we're overcomplicating things, but when you do your long division, it makes things a lot easier. So my dividend is 3/2 x plus 0, and my divisor is x minus 1/2. So I'm only going to look at the first terms in both polynomials, and you see that 3/2 x divided by x is 3/2. So if I multiply that through, I end up with 3/2 x minus 3/4. Now I'm going to subtract that entire polynomial from the one above it. So this first term is going to reduce to 0. I might as well put that. And then I have 0 minus a negative 3/4, which is going to turn this into a positive 3/4. So if I rewrite this f of x, I have f of x equals the quotient 3/2 plus the remainder 3/4 over the divisor x minus 1/2. And as I did in the previous example, I'm just going to rearrange the furniture a little bit here using the commutative property of addition, and I'm going to say that I've got 3/4 over x minus 1/2 plus 3/2. Makes it a little bit easier to see the translations. So our k is 3/2. That means we're going up 3.5 or 1.5 units. And right here, we're subtracting 1/2. That means our h is 1/2. That means we're going to the right 1/2 units. And we have compression by 3/4. So our vertical asymptote is going to be at x equals 1/2 or 5/10, and our horizontal asymptote is up 1.5 units. So the first thing we're always going to do is graph our asymptotes. We are shifting up 1.5 units, and we're shifting to the right 1/2 unit. So the scale on this is 1/2 per division, and we're really looking for what's happening around that point of intersection. To figure out the effect of that compression by 3/4, probably the easiest thing to do is going to be to go ahead and make that table of ordered pairs. So I'm going to say x, and I'm just going to look at some points around that point of intersection. Our output, I'm going to go back to the original. It's a lot easier to deal with. 3x over 2x minus 1. So if I take a look at, say, 1 unit to the left here, x equals 0, if I substitute x equals 0 in, that's going to turn the entire numerator into 0, and 0 divided by anything is 0. So right here, we are expecting to go through the origin. Let me put that in red. And likewise, if I look 1 unit to the right of this intersection at x equals 1, if I plug that in, that's going to be 3 times 1 is 3 divided by 2 minus 1, which is 1. So that's going to equal 3. So at x equals 1, we're going to be up here. And you're looking for that symmetry. So I moved over a half, up 3. I moved left half, down 3. So that's exactly where we should. Now to get a few more points, you can try moving to the left and to the right another unit. So say at x equals negative 1, I would substitute that in. That would give me negative 3 in the numerator, and I would have negative 3 in the denominator, so that's a positive 1. So at x equals negative 1, I would expect to be here at 1. And I'll try moving to the right one, so that would take us over to 2. So that would be 6 in the numerator divided by 3 equals 2. So I would expect to be at 2. So you can clearly see that our reciprocal function is going to kind of bend in here and over here. Because I'm kind of missing this point in here, I'm gonna look at 2 additional points. So I'm gonna evaluate at negative 1/2 and positive 1.5 or 3/2. So if I put those in there, I've got negative 3/2 in the numerator divided by, let's see, negative 2. And that would give me a positive 3/4. And if I put in positive 3/2, I will have positive 9/2 in the numerator divided by 2, which is 9/4, or 2.25. Okay, so if I graph those, at negative 1/2, I'd be up at 3/4. That would be right there. And 2.25 would be right here. So you can see the symmetry. The reciprocal function in the upper right is going to just approach those asymptotes, and it'll be symmetric over that point of intersection here. All right, 2 more examples, and this time we are going to see what effects come about when you're able to factor. Both of these examples are in fact reciprocal functions in disguise, even though we don't necessarily have a linear function in the denominator or even in the numerator down here in this example. In these 2 examples, I'm going to be talking about something called holes, and that is a point of discontinuity in the graph. Okay, so let's go ahead and look at this example. We're always going to want to factor out. So in the numerator, I can see 2 times x plus 4, and in the denominator, I have a equal to 1 here. So a times c is negative 8. I'm looking for 2 numbers that multiply to give negative 8, that sum to give positive 2, and you can see that that would be x plus 4 times x minus 2. And right away you can tell that we have the x plus 4s are going to reduce out to 1. So I can rewrite my function as 2 over x minus 2. Now right here you can see that our k really is like an invisible plus 0 here. So there is no shift vertically. And we have a subtract 2. That means we're going to the right 2 units. And we also have some stretch here. We have stretch of a factor of 2. So that's going to give our vertical asymptote at x equals positive 2. And our horizontal asymptote is going to stay the same as the parent. So that's going to be the x-axis, or equation-wise, y equals 0. So to graph, as always, we are going to graph our asymptotes. So we're at the x-axis like the parent, and our vertical is x equals positive 2. So our point of intersection is right here. We don't have a reflection, so our reciprocal function is going to be over here in the upper right and over here in the lower left. So if I make a little table and get some points, I've got maybe go to the left 2 points, to the right 2 points, so maybe look at 0 and 1, and then 3 and 4. And I have 2 over x minus 2. So if I put in 0 there, I'm going to be at an output of negative 1. If I put 1, I'll have negative 2. If I put 3, I have 2. And 4, I have positive 1. So I can graph these points. And I'll go with the 0 first. So I'm here at 1, I'll be at negative 2. And on the other side of the intersection, at 3, I'm up at positive 2. And 4, I'm at 1. And you should see that symmetry. But here's where the hole comes in. So at x equals negative 4. So if you look back here, remember when we had to identify the domain of rational functions, we would always have to exclude all the domain that would create a 0 in the denominator, even though this factor did cancel out or reduce to 1. Same thing here, same thing applies. At x equals negative 4, we would have a problem. We would have an undefined output. So if I take a look at what my output is at negative 4, I have 2 over negative 6, which is negative 1/3. All right, so if I zoom in here and see where that point of discontinuity is going to be, right here is a half. So 1/3 is less than that, so maybe I'll be like right in here, I'm going to have a hole. So my reciprocal function is going to approach my asymptotes, but right there I have an undefined output. So we call that a hole or a discontinuity in the graph, mainly because the output is undefined. So think of the piecewise functions we did in the beginning of the year, where we had some holes on the graph, very similar here. All right, and just to finish this problem, I will finish the rest of my reciprocal function over here in the upper right. Okay, one last example here. This time we have quadratics in the numerator and the denominator, and we are going to factor that. The top is a difference of squares. So I can factor that into x plus 3 times x minus 3. And the denominator, again, a is 1, so I'm looking for 2 factors that multiply to give negative 15, that sum to give negative 2. So that would be x plus 3 times x minus 5. And we can see one set of x plus 3 factors will reduce out to 1. So I have f of x equals x minus 3 over x minus 5. And here we have 2 linear polynomials, so we're going to have to use our long division. So my dividend is x minus 3. My divisor is x minus 5. We're only paying attention to the first terms in both polynomials. X divided by x is 1. I'm going to put that over its like term. Then I'm going to multiply through, and I have x minus 5. And I'm going to subtract this entire polynomial. So x minus x is 0. Negative 3 minus a negative 5 would be negative 3 plus 5. So that is positive 2. So I can rewrite my function as f of x equals the quotient plus the remainder over the divisor. And I'm just going to rearrange the furniture a little bit using the commutative property of addition. And I see that I am shifting up 1, k equals 1. So I shift up 1. And I'm subtracting 5, so we're going to the right 5. And we have a stretch again of 2. So if I am shifting to the right 5, x equals positive 5 is going to be my vertical asymptote. And shifting up 1, y equals 1 is going to be our horizontal asymptote. All right, so I am going to graph my asymptotes. And I have x equals 5 and y equals 1. I don't have a reflection again, so I know that my reciprocal function is going to be over here in the upper right and over here in the lower left. I'm going to make a little table of ordered pairs. So I've got x and f of x equals 2 over x minus 5 plus 1. So going maybe again 2 to the left and 2 to the right, if I plug in 3 and 4 and 6 and 7. For 3, I have 2 over negative 2 would be negative 1 plus 1 is 0. I have 2 over negative 1, which is negative 2 plus 1 is negative 1. 2 over 1 is 2 plus 1 is 3. And 2 over 2 is 1 plus 1 is 2. So I can graph these points, making sure that I have symmetry. 2 points over here, and 6, 3 up here, and 7, 2. So we're looking for symmetry about that point of intersection, and we have it. We do have to pay attention to holes, and we are going to have a hole at x equals negative 3. So right there, even though that factors out, or I'm sorry, reduces to 1, we're still going to have a hole there. So I want to look to see where is that output going to be at negative 3. That would be 2 over negative 8 is negative 1/4 plus 1 is going to be positive 3/4. And unfortunately, I didn't leave enough room on this graph in order to graph that hole. So we're going to be approaching the asymptotes, and we would see a hole had I allowed the graph to continue to the negative there. We would see a hole at x equals negative 3. Okay, this video turned out to be kind of long. We had some complexity to deal with in searching for reciprocal functions when it's not obvious one exists. We use long division as well as factoring to kind of put some of these rational functions into a reciprocal format so that we could see the translations which directly tie to the vertical and horizontal asymptotes. And finally, we learned how to look for holes, and those would be the area on the curve that results in an undefined output. Okay, thanks for listening.